Welcome to The Explainer. All right, today we're looking at something that is honestly, truly mind-bending. We're going to unpack the thrilling mathematical cheat code required to literally leave our planet. I mean, have you ever actually stopped to wonder what it takes, by the pure hard laws of physics, to break the invisible chains of Earth's gravity forever? We aren't just going to geek out about rockets today. We're going to dive right into the elegant foundational math that dictates our very freedom to explore the cosmos.
So let's dive into this with a highly counterintuitive fact. Get this, as you sit or stand there watching this explainer right now, your gravitational energy is mathematically negative. Yeah, negative. It sounds completely bizarre, right? But to understand how we actually escape Earth, we first have to understand the really strange nature of the ground we're standing on, and this sort of invisible energy well we're currently trapped inside. To make sense of this whole negative energy thing, let's establish a quick baseline. Potential energy is simply the energy stored in an object because of its specific position or physical state. But the absolutely crucial phrase here is relative quantity. You see, potential energy isn't absolute in the way that, say, mass is. It changes based entirely on the reference frame you choose. It's all about where you are compared to a very specific 0 point.
And you know, this brilliantly illustrates the difference between our everyday experience and the wild reality of space. For low altitudes, like say you're just tossing a baseball up in your backyard, the height from the ground is incredibly tiny compared to the sheer size of Earth's radius. So we just assume the acceleration due to gravity, g, is a constant 9.8 meters per second squared. We use that simple, familiar formula you might remember from high school: mass times gravity times height. In this everyday scenario, the literal ground beneath your feet is our 0 point. But when you move to massive, orbital heights, gravity is no longer constant. It continuously decreases the further out you go. You just can't use ground level as your 0 point anymore when you're dealing with the scale of an entire planet.
So if we can't use the ground, where is 0? Well, physics designates infinity as the absolute reference point where gravitational potential energy is exactly 0. Imagine zooming out, way out, moving an infinite distance away from Earth. Out there in the deep void, Earth's gravity drops to exactly 0. It literally no longer binds you. That infinite, empty distance is our cosmic zero-energy surface.
Now, what's really fascinating is how this completely resolves our initial hook. Think about it. If your energy increases as you move outward away from Earth, eventually hitting 0 all the way out at infinity, what happens when you move in the opposite direction? Moving inward from 0, back towards Earth, means you are dropping below 0. Because you have to reach 0 at infinity, any finite distance closer to Earth must logically, mathematically start at a value less than 0. And that is exactly why your gravitational potential energy is always negative at finite distances. You are, quite literally, sitting at the bottom of a negative energy well.
All right, let's move into Section 1, the mechanics of escape, breaking the pole. Let's start with a simple projectile thrown vertically upwards. You give it an initial upward velocity, right? But immediately, almost the second it leaves your hand, that velocity is continuously depleted by Earth's downward gravitational acceleration until it eventually hits 0. At that exact split-second moment, it reaches its maximum peak height before inevitably falling back down. This is all calculated perfectly using Newton's third equation of motion. Naturally, if you increase that initial launch velocity, the peak height increases too.
But here's where the magic really happens. Because gravity is proportional to 1 over the distance squared, it scales down as the object climbs higher. This means the downward pull gets weaker and weaker the further the object travels. It's like Earth's invisible tether is stretching and thinning out. If your initial velocity is high enough, you can actually completely outpace this diminishing pull.
Which brings us to the main event, our ultimate goal: escape velocity. This is the minimum initial velocity required to permanently escape Earth's gravitational influence and never fall back down. Basically, to break free entirely, you have to launch with such immense speed that you reach that infinite distance we talked about earlier. By the time you reach infinity, your net velocity finally hits 0, and you come to absolute rest.
Okay, on to Section 2, the ultimate calculation, conservation of energy.
This whole concept sets up a really elegant balancing act. The law of conservation of energy tells us that the total mechanical energy in a closed system must remain constant, so E1 must equal E2. Think of E1 as our energy profile right at the moment of launch, sitting on the surface of the Earth. E2 is our energy profile at an infinite distance away. Now, at infinity, our kinetic energy is 0 because we've come to rest, and our potential energy is 0 because we're entirely free of Earth's gravity. Therefore, our total energy way out there, E2, is exactly 0.
So the absolutely crucial point here is how we set up this equation. If E2 is 0, then E1 must also equal 0. Here on Earth, our total energy is our positive kinetic energy at launch, which is 1/2 mass times velocity squared, combined with our negative gravitational potential energy. So 1/2 mv squared minus big G big M little m over r equals 0. We are literally equating the massive violent burst of energy at launch directly to that absolute zero state of perfect stillness in deep space.
Okay, I absolutely love this next part. It's one of my favorite details in all of orbital mechanics. When you balance the equation by moving the potential energy to the other side, notice the lowercase m, the mass of the escaping object, it's on both sides of the equal sign, which means it cancels out entirely. This is profound, guys. It means the exact speed required to escape Earth is identically the same whether you're launching a tiny little pebble or a massive million-pound starship. The escape velocity relies solely on the mass and radius of the planet you're trying to leave, not on the object itself.
So we do a little algebra, isolate for v, and we get our final derived formula. Escape velocity equals the square root of 2 times the gravitational constant times the mass of Earth divided by the radius of Earth. Or to make this even easier to solve, we can substitute standard gravity, g, right into the equation. Since g equals gm over r squared, the math beautifully simplifies down to this highly elegant formula, the square root of 2 times g times r.
All right, all that's left is to actually run the numbers. We just plug Earth-specific standard constants into our shiny new derived formula. We know our standard acceleration due to gravity is 9.8 meters per second squared, and Earth's radius, that's roughly 6.4 million meters. So 2 times 9.8 times 6.4 million. We multiply all that together, take the square root, and, drumroll please, we arrive at our final answer.
Boom, 11.2 kilometers per second. There it is. That is the ultimate critical speed limit. A spacecraft or projectile must hit exactly 11.2 kilometers per second at the exact moment of launch to completely break free from Earth's negative energy well and drift into the zero-energy expanse of infinity forever.
It's just such an awe-inspiring number. I mean, it literally represents human ingenuity overcoming the sheer forces of nature through math. But, it also leaves us with a pretty provocative thought. If it takes a staggering 11.2 kilometers per second just to escape our own little blue marble, what kind of cosmic speed limit do you think we have to break to escape the unimaginably massive gravitational well of the Sun and leave the solar system entirely? Definitely something to ponder the next time you're looking up at the stars. Thanks so much for joining me on this explainer, and hey,